Hello, welcome to this video. So in this video we're going to be looking at finding the integral of 1 over x. The formula is usually given at A level for the integral of 1 over x, but it's rarely explained, so we'll be looking at how we would work out what the integral of 1 over x is without being given the kind of formula, and we'll particularly be looking at what logarithms have to do with this and why logarithms appear. So this is going to be a kind of casual proof of why the integral of 1 over x is equal to log to the base e of x. So essentially we'll be looking at how we get this, how we go from an integral of a polynomial like 1 over x, and how we end up with a logarithmic function of x, because at first logarithms and polynomials don't seem to have much to do with each other. And I'll be doing this proof just using stuff you learn in A-level maths. I won't be using any stuff from further maths or any maths beyond that. So this will be a nice kind of casual proof, which will hopefully be accessible to lots of people, and will help show where logarithms enter into this. For more kind of formal proofs, you could look at things like Taylor series or other things, but I'm not going to do that. I'm just going to use stuff from Maths A level and try to keep this nice and light, and really explore the mystery of how this logarithm appears. So the first trick, if we're trying to work out what the integral of 1 over x is to look at the solution and go, okay, if we want to prove this result, what clues do we have from the solution about where to start? Well, the solution says that the integral of 1 over x is the logarithm to base e of x, or log of x. But logarithms are quite hard to deal with, so let's start by thinking about exponential functions, which is the inverse operation to logarithms, because they're inverse relations, logarithms and exponentials are related, but exponentials are a lot easier to deal with, they're a lot easier to differentiate. It makes a lot more sense how to integrate them, so let's start by exploring exponentials, and this will give us a way in to hopefully using logarithms later on in the proof. So in summary, we have logarithm to base e of x as a solution, so let's think about the properties of a related but simpler function, which is e to the x. So what special property does e to the x have? Like, if we're thinking about e to the x, what makes e to the x special? Well, the special thing about e to the x is that if we differentiate e to the x, we get back e to the x. So if y is e to the x, then the derivative of y with respect to x is e to the x. So it's a graph where if you plot it, every point on the graph, the y value of that coordinate is equal to the gradient of the graph at that point. So because of this, we can actually define y equals e to the x to be the solution of the differential equation dy by dx is equal to y. And that's because we've said if y is e to the x, then dy by dx is equal to e to the x, but e to the x we've just defined to be y. So because we've started with if y is e to the x. So in summary, y equaling e to the x is the solution to the differential equation dy by dx equals y, and what we're going to try to do is solve this differential equation and for a while forget that we know the solution being y is equal to e to the x, and then we'll make use of the fact that we do know the solution at the final stages of this proof. So keep in mind the fact that the solution is y is equal to e to the x, but now we're going to try to solve dy by dx is equal to y without knowing what the solution is beforehand. So how do we solve dy by dx is equal to y, assuming we don't know what the solution is? Well, so we're gonna, as I said, pretend that we don't know the solution, and we're going to try to solve this differential equation. So how can we solve it? Well, because of the way that this equation is organised, we can rearrange it to get all y terms on one side and all x terms on the other. And this process is called the separation of variables, and it's really useful with differential equations like this where we have just a first order derivative. So often first order differential equations, so differential equations with just a first order derivative, can be solved using the separation of variables. So we're going to do that to this equation to solve it. So here we go about solving dy by dx is equal to y. So we firstly rearrange things a little. Now here I am slightly cheating. I'm acting as if dy by dx is a fraction, when in reality it's the result of acting a derivative operator on y. So it's really a map from y to dy by dx. It's not actually a fraction. However, the way that a derivative is defined is it is defined as a fraction where we then take a limit. And so, in some sense, it still has fraction-like properties. And so I'll make use of that here and pretend that dy by dx is just a usual fraction like a over b. So we can move the dx to the right-hand side of the equation, and we can divide both sides by y to bring the y to the left-hand side of the equation, and that way we get 1 over y dy is equal to dx. Now we want to try to make sense of this, because at the moment we've got 1 over y dy is equal to dx, and that's not much more informative than dy by dx is equal to y, so we haven't really done much in terms of solving it yet. But by getting all y terms on one side and x terms on the other, we can now do a useful trick where we can integrate both sides, and because one side is just in terms of y and the other side is in terms of x, we can make sense of these integrals quite easily. If we were trying to integrate something that had y terms and x terms, you can imagine it might get quite complicated, particularly as y and x depend on each other. But now we've separated y terms on one side and x terms on another, we can kind of reasonably elegantly integrate both sides. And integrating will get rid of a dx, and I'll show you this now. So we integrate both sides like I said, and we end up with the integral of dx. So let's deal with that. So by dealing with the integral of dx, we're going to simplify this expression a bit. So we can simplify things a little, as I said, by integrating dx. But at first it might look like, how on earth do we integrate dx? Because you're used to integrating a function of x in terms of x, but how do you just integrate in terms of x without there being a function present in the integral? two ways. One way is to go back to what an integral really is, and that way we can evaluate the integral of dx immediately. But another way, kind of trick if you like, is to think about the integral of dx as the integral of 1 times dx. But because 1 times dx is dx, the integral of dx is also equal to the integral of 1 times dx, and the integral of 1 times dx is equal to the integral of x to the 0 dx, because x to the 0 is 1, and when we integrate x to the 0 we just get x to the 1 divided by 1, which is just x. So in conclusion, our solution to the differential equation dy by dx is equal to y is the integral of 1 over y in terms of y is equal to x. So we've gone as far as we can pretending we don't know what the solution is. But as we said before, we know that the solution to the differential equation is y is equal to e to the x. So let's now make use of that knowledge. So we know the solution of dy by dx is equal to y is equal to e to the x. But if y is equal to e to the x, then taking logarithms of both sides, we can see that x must be the logarithm of y. And if we substitute x for the logarithm of y, what we end up with is that the integral of 1 over y in terms of y is equal to the logarithm to base e of y. So in short, we have proved that the integral of 1 over y dy is equal to log to base e of y. But the universe doesn't care whether we use y or x, so if it's true for y, it will also be true for x. So we could also say that the integral of 1 over x in terms of x is equal to log to the base e of x. So in conclusion, we have proven what the integral of 1 over x is, or 1 over y is. And we did this by thinking about a simpler but related function to logarithms, that is the exponential, thinking about the core property of the exponential as a solution to the differential equation, for a while forgetting we knew the solution and trying to solve the differential equation, and then substituting the solution back in, and then we end up with this. So the main goal is, if you don't know how to solve something, look at the answer, if you have the answer, and think, well, using the answer, what clues are there within the answer? For example, in this we can see that there's a logarithm, so we took the hint to use a related function, hoping that we could use logarithms later on, and so we used the exponential function. But ultimately maths is kind of games and puzzles, so the main kind of advice I can give is essentially, if you're not sure how to do something, just play around with it, but do try to take hints from the solution if you have the solution, and that way you'll find your way to the solution hopefully a lot easier. So thank you for watching this video. If you found this video helpful, please do check out my other videos, and I hope to share with you some more wonderful maths or physics soon.